Ladies and gentlemen, good morning. We will start our annual conference core 2024. My name is Jan Milčák. I'm working in the CVR as a director of reactor operations section, and at the same time I'm the member of board of directors. It's my pleasure to welcome you in our conference core 2024. I'm very happy that this tradition since Susan conference since 2018 are still set. And such annual meeting is still well attended. Let's take this conference as an opportunity to share knowledge on select topics. For this year, we select topic the radioactive waste, but not only this one. For today, the main chair and the main facilitator will be Jana Kalivodová. Today, the topic will be presented in several contributions during the morning session. Few presentations for this selected topic. The afternoon program will continue with the presentation of our research infrastructure, CISR, and the possibilities what to do with that, and the examples how the infrastructure has been used and utilized. For tomorrow, we prepare a day for a visit to our infrastructure, LVR 15 hot cells, and if somebody is really attracted to, we can go with a little bit other places. Please take this conference as an opportunity to come together again, to share knowledge, to explore latest advancement in our field. During the day, we will have presentation, but also please take the opportunity of our coffee breaks, lunchtime, and the spare part to networking and discuss with other colleagues from other fields. I would like to extend our special welcome to speakers, not only those who are presented here, but also for our online presenters. Also like to welcome all the attendees here directly and our listeners online. The direct presence of so many people here in the hearing room and the online means that what we are doing makes sense. It shows the general interest in our field, what we do, and also means that we can share the benefits of research and what we do. I also want to thank the organization team, Jana and others, to prepare the conference and all the efforts which we put to ensure the smooth preparation and organization. So we have exciting agenda here in this. We have networking opportunities. We have also poster sessions on the upper parts, especially for those who are interested in the, how to call it, students' work, looking for some job as a first-timers. So I encourage you to take full advantage of our conference to make it like the best time of the year. So thank you again here, and I'd like to ask Jana to facilitate the rest of the conference.
Thank you very much for introduction to Jan Milčák. It's our honor to start our annual conference. I welcome you all here, also our participants who are online. As already said, there will be a lot of place and opportunity to discuss and talk about your results and work. In this respect, I would like to say that we will have always 20 minutes, about 20 minutes presentation, and then please keep the question for the end of the presentation. After each presentation, you can give some question. We will have also some time later on for wrap-up and discussion in the end of the conference. As already said, I thank very much to all people who participated in the preparation of this conference, scientific committee team, and the chairman and our director for strategy, Danes Burkett, and Honza Milčák, of course, but also to our communication support team and all people who makes this possible, this event. So with that, I would like to go to first presenter. It's a big honor to have here Mr. Frank Fasten. Sorry for reading, but his CV is really rich, and I would not like to make any mistake, and I would like you to know everything who is going to give our first speech. So, Frank Fasten is senior expert at the EC Joint Research Center, holds his PhD in nuclear chemistry, and has more than 35 years of research experience in various nuclear fields, from condensed matter physics, chemistry of actinide elements, nuclear fuel cycle, reactor safety, emergency preparedness and response, nuclear safeguards and security to nuclear waste management and decommissioning. Frank contributed to more than 250 scientific peer-reviewed publications and reports. One very important for latest development of the Europe is the technical assessment of nuclear energy with respect to the to do no significant harm criteria of regulation, so-called taxonomy regulation report, very important one for us. And he was previously head of knowledge of nuclear safety and decommissioning unit in GRC Patent, and then he moved 2023 to GRC Directorate, Nuclear Decommissioning and Waste Management, within which he is today responsible for nuclear decommissioning and waste management program. This one is, has sites in Patent, Karlsruhe and Hell. So I hope that we have Frank online and he is ready to tell us something more about his work and waste and decommissioning in Europe.
Yeah.
Thank you very much, Frank, for accepting our invitation. We are really honored. Hello.
Yeah, thank you, Jana. Good morning, everyone. I will start sharing my my screen and the presentation. I will see if it appears on your big screen. So now it's shared. Do you see it? Can you hear me? Jana, can you hear me?
Yes, we can hear you. Thank you very much. So we see the first page of your presentation. Just let me just...
Okay, so you see the presentation also, because I don't see it on the screen.
Sorry?
You see the presentation also?
Yes, yes, we can see, and the slides are moving, so it will be
okay,
fine.
Perfect.
Just
perfect.
Please speak up. Apparently, our system is not. So please, a little bit louder.
Okay.
Thanks.
So I go ahead. So very quickly, I want to start recording some facts and figures about the Joint Research Center. So the Joint Research Center is the Directorate General of the Commission. You have here the today until next week commissioners in charge of the GRC. Our Director General is Bernard Magnan, acting for the moment. And the GRC is composed of several directorates. And I have highlighted the two directorates which are in charge of the nuclear program. So the directorate, so-called Directorate G, Nuclear Safety and Security, led by Mrs. Ulla Engelmann, and the Directorate J, Nuclear Decommissioning and Waste Management, led by Laurent Gérige. I will go a little bit into more details later on in the difference between the two directorates. So the mission of the JRC is to provide independent, evidence-based knowledge and science supporting EU policies. We are the service of scientific service of the Commission, with both missions, so serving the policy of the EU and also conducting our research program from our own so-called direct actions. So the headquarters of the GRC is in Brussels, as one could have expected, and we have we are located in 5 sites in Belgium, Geel, Germany, Karlsruhe, Italy, Ispra, the Netherlands, Petten, and Spain, Sevilla. 4 of them have nuclear activities. So the Petten hosts the high flux reactor and nuclear material research. The Gale site is mostly accelerators, and Karlsruhe is dedicated to the fuel cycle. At Ispra site, all nuclear installations are in decommissioning process. We are owning a budget directly from the Horizon 2020 in the so-called direct actions, and from the Euratom program. So overall, the GRC is a little bit less than 3,000 staff located in the different space I mentioned before. And we are hosting more than 50 large-scale research facilities, as I mentioned, such as the HFR and the accelerators in Geel and the hot cells in Karlsruhe. We do a lot also in support for our training. One of the major worries for Europe today is to, in the context of the, let's say, the renewal of the interest in nuclear energy, is to dispose of the necessary skills and talents. And we are acting, as it is said on the slide, as a catalyst to share knowledge with different nuclear stakeholders. We are also trying to be part of the different networks and making the bridge between research in the labs and science-based policy, and also raising awareness on initiative, skills, and competence in nuclear. What I want to present you in the second part of the talk is what we are doing in nuclear decommissioning and waste management, particularly not only at GRC level, but more broadly at the level of the Commission. I will start with the GRC itself, so where the main highlight are research activities, scientific support, as I mentioned, but also operational decommissioning. And it is in this part that I'm today active. From the research point of view, the program, the ongoing program, puts the accent on 3 main portfolios. So research and policy support in small modular reactors. The second one is the safety of nuclear technology in support to the transition towards climate neutrality. And finally, support to nuclear compliance assurance, which embeds also the nuclear safety and security. The directorate which is leading in this context is the Directorate G in nuclear safety and security. The headquarters is located in Karlsruhe, although the directorate is spread over all nuclear sites I mentioned before. The accents of our activity are in radioactive waste management from the research point of view, nuclear knowledge and competencies, non-power application and radiation protection, in particular radiomedical applications, and nuclear power plant safety. That's globally for the nuclear safety side, and we have also activities in nuclear safeguards, non-proliferation, and security. The operational decommissioning is a task is performed in Directorate J. The headquarters is in Ispra, and it concerns the 4 nuclear sites with different facilities that I mentioned. To note that, as I said, in Ispra, all the activities, nuclear activities involving nuclear materials are being phased out, and so we are proceeding to the operational decommissioning of the different installations. In Karlsruhe, we prepare the decommissioning plan. The site, the different sites of the GRC have an agreement with the hosting member state until around 2060, but it's time to be ready to secure the financing and the decommissioning plan for all the sites, although an extension could be possible, but we are speaking about a long-term future. In Pétain, we are mostly working on the decommissioning plan of the high flux reactors. The high flux reactors should be replaced around 2030 by the in construction Palace reactor to take over the mission of the HFR, which is more older than 60 years now. And in Gale, we are speaking about the accelerator Jelena and Van de Graaf in on site, also keeping active until 2060. Another important part of our work is in knowledge management for nuclear waste, nuclear decommissioning and waste management, for several reasons. So it's a long process. Our staff are aging, of course, and we have now we are entering the fourth generation of scientists working in our installation. So there is a risk of loss of knowledge of the history and also technical knowledge of the different installation. So this called for an extensive work on ad hoc documentation. We are responsible accountable and need to be transparent of the different work we have done, and to share the knowledge which is gained through the experience with the member states and other different organizations. How do we proceed? Well, here you have a snapshot of the methodology that we are using to collect the knowledge and to make it available. So of course it starts with identifying and capturing the knowledge inputs that is available, to categorize it, to store it in a safe and secure way, and to develop so-called knowledge products, summarizing the knowledge that is now available on different topics. And most of all, the knowledge which is not shared is completely useless. So how to share and monitor the knowledge product and measure the impact they have. So one of the important pillars for knowledge management is to be able to share it, and therefore we are regularly organizing events to disseminate knowledge and try to participate in high-level workshop and conference to develop ties with across the EU. Just to highlight, we also organize summer schools, and the next summer school on nuclear decommissioning and waste management will be in Ispra in the week of the 23rd June 2025. So that was for the main action of the GRC, without entering into too much technical details. I will speak now a little bit about DGNR. So DGNR is the Directorate General in charge of the energy policy in the Commission. A part of it is dealing with nuclear energy, mostly located in Luxembourg. And it is in charge, more particularly also, of the European legislation related to safety safeguards in the nuclear safety and safeguards in the member states. So it is responsible for the main directives related to dismantling, so waste directive, waste management directive, and spent fuel. The basic safety standards, the nuclear safety directive, and it is also financing the so-called nuclear decommissioning assistance program. So the nuclear decommissioning assistance program has been decided following the Chernobyl disaster and during the extension of the Commission at this, of the European Union. At this time, it has been requested that Bulgaria, Slovakia, and Lithuania shut down their old Russian-type reactors, and to support this operation, a nuclear decommissioning assistance program was established, and a dedicated financial envelope allocated to support this program. Today, this program also embeds the objectives and financial envelope for the decommissioning of the JRC owns facilities. Besides that, the Council regulation which mandates which support these nuclear decommissioning assistance programs also mandates the JRC for knowledge dissemination objective and duties, as I mentioned before. Another key partner is DG RTD that probably most of you know in details. So the DG RTD is responsible for the so-called indirect action. So this is the Euratom research program funded by the Commission, but carried out by a member state organization. To which also associated countries can participate, and those one takes form under the shape of multi-partner consortia. In the field that interests us today, I will mention EURAD 2. So EURAD 2 is the European research program on nuclear waste management, except decommissioning. So here we're speaking really about the nuclear waste management. It developed a vision, roadmaps, and strategic research agenda, as well carrying itself strategic studies and some knowledge management activities. So just to mention also that EURAD facilitate mobility action also for associated member states, and I took the example of Ukraine in this context, especially because of the situation that we have now in Ukraine. Last but not least is the so-called DG INPA. So DG INPA is responsible for the international partnership. It addresses mostly to support third countries on candidate countries, European Union neighborhood, and also worldwide. It's very important also in the context today, as several countries outside the EU are looking also at embarking in nuclear energy. We are speaking about countries in Africa, or in Asia, and not well conducted nuclear program in such regions could have indirect impact on the overall nuclear policy worldwide. So it's why the Commission is supporting the countries to improve their the safety, security, and safeguard principle, which have to be applied in the nuclear programs. It addresses also supporting countries to get rid of their nuclear liabilities, and is leading the initiative of nuclear safety cooperation in the different countries. Here we are speaking about a rather large budget. As an example, it's DG INPA which supported the entombment of the Chernobyl reactor after the accident. In this context, the Instrument for International Cooperation in Nuclear Safety, as you see, is spread over several pillars. Promotion of an effective nuclear safety culture for about half of the program. The responsible and safe management, which completes the second half, and some less dominant action in safeguards and measures for support. The idea is to transfer to the different countries the knowledge and gain in the EU and international best practices, and also in the case of neighborhood and European Union extension, to share and align the countries with the so-called European Union acquis. In this context, I would highlight the different programs in cooperation and education, which are conducted by different consortia and aim at look at nuclear skills, not only from a technical point of view, but also from leadership, management, program management, and soft skills, which today might be even the main bottleneck in the progress of nuclear projects, and particularly development of SMRs and new power plants. So it seems that I'm relatively fast. I hope I have not been too fast. So I have tried to give you some insight of what the JRC and the Commission is doing, and to share and demonstrate that we remain committed to working together with partners to improve nuclear safety in decommissioning and in operation and in research of the different nuclear programs, and the importance that we are giving to education and training, as well tutoring projects to support the sustainability of skills, competence, and talent in nuclear. I try to give you also an overview of the different DGs and which part they are leading in this context, and demonstrate that our program is also open to external organizations from the EU, in particular the direct neighborhoods. With this, I thank you for your attention and be ready to answer your questions. Thank you very much.
Okay, thank you, Frank, very much for your presentation. Great introduction to our topic. What is very important also for our institute and other organizations dealing with the research in nuclear is to have overview and connection with the DGs, different DGs, because in the end of the day you are writing the work program for us, and we can participate on projects, and we can collaborate all together and have nice results in all the area, especially the area of radiological waste and decommissioning, which is an important part of the nuclear. So I would like to ask if there are some questions in our room. It seems that it's the beginning of the day, everybody is shy, so for this moment there are no questions. I also haven't seen any on the website. Or yeah, there is, okay, there is one. Perfect, I'm coming. Mr. Uhlir,
So hello, Frank, here is Jan Uhlir. So I have a question concerning the situation of NRG Palace reactor. So it will be probably a reactor of the owned to Netherlands, yeah? So how it will be the possibility to use the reactor, yeah? Because original reactor was only operated by NRG, but it was in ownership of European Commission of Euratom.
Correct. So the HFR, for those who do not know, is indeed owned by the Commission, and was also supported by a so-called supplementary program to operate and facilitate access to researchers. The HFR will be shut down in as soon as let's say the construction of Palace has been completed. Palace has been a long story. It is an initiative of the Dutch government, so the Netherlands, and unfortunately, at that time the decision has been taken. There was no discussion to make it a European installation, so it's owned by the Netherlands. It's under the leadership from tomorrow on of the Ministry of Health in the Netherlands. And for the time being, beside involving Palace through indirect actions and different supports like PRISMAP or a program for the radionuclide productions for medical applications, there is no today real European program associated directly to Palace. Nevertheless, we are in touch with the ministries, and our DG, Mr. Bernard Magenan, will meet with the different ministries in the Netherlands not later than the 11th of December. And we are going to propose the Netherlands to, let's say, to develop a concept for a better and more availability to the community of the European Union. So it's a process ongoing, and I hope we will be successful in this context. I hope I have answered your question.
Okay, thank you very much. Thanks for that. I thank you one more time for your presentation, and we hope that we can, for example, meet in broader school, for example, what you were presenting to us. We will, of course, spread between our colleagues
yes,
all the possibility for this common events, and we will be happy. Looking forward.
If you want, Anna, I can, when the dates and more details on the different organization of the events we are organizing, I can send you an email with the links that you can distribute amongst the community.
That would be great. Thank you very much. And thank you for your presentation.
Thank you.
Okay, have a nice day, and stay with us if you can, because you can learn.
I will stay with you.
Yes, yes, you can learn what we are doing here and our colleagues, so it will be a pleasure. Okay,
thank you.
So there we can move on to the next presentation. We are a little bit ahead, so we don't have to hurry, but we are not going to stand. So next presenter is Mr. Michal Cihlář. He's coming. He's also employee of CVR, in the same time still active young student at the Czech University. Okay, and he's going to tell us something about the fuel processing and fluorine chemistry. I stop here, Michal. Please, floor is yours.
So, good morning. As it was mentioned, my name is Michal Cihlář, and together with my colleagues, with Jan Uhlíř and Martin Mareček, we prepared this presentation for you. But even before I start with my presentation, I would just continue with the previous presentation, because I had the opportunity to attend the summer school about the decommissioning that was mentioned a couple of years ago, and it was amazing. So highly recommend it. If anyone thinking about that, then definitely go for it. Also, my presentation continues with the previous presentation, with the spirit of like the overview of the work that we've been doing with my colleagues, and with many more colleagues that are workers in the Research Center Řeč, or have been previously working in CVR, UJV, or Research Institute before. So the basic outline, I will talk about 3 topics. First, about the fluoride volatility method that was being developed here CVR and previously. Also about the technology for uranium, plutonium, and americium removal from the Fukushima fuel debris. And at the end, about the fuel cycle and its technology for molten salt reactors, and also the work that being done here in Czech. So the fluoride volatility method, it's the technology that's based on the direct fluoration with the gaseous floor of the spent fuel. The separation process is based on the property of the uranium, neptunium, and also a little bit on plutonium, it forms volatile hexafluorides, and most of the other fission products and elements that we have in the spent fuel do not. So we can separate them by this method. It was originally mentioned for the use with the fast breeder reactors, but also then it was realized that it can be used in other processes. So here is the basic flow sheet, where the main part is at the it's not seen. Okay, at the beginning, with the fluoration and the fluorination reactor, and then with the different condensers, different parts are separated. The development of this fluoride volatility method was here in Czech, happening since 1980s. Of course, in that time in the Nuclear Research Institute, then in UJV Řeš, and it continued in CVR later. It was a part of at that time, Czechoslovak and Soviet program for the development of this pyrochemical reprocessing for the fast reactors, as it was mentioned before. And in the past 30 years, it was continued, and the main focus was on the optimization of some selected steps, with the main emphasis on the fluorination and the fluorine reactor. So, as I mentioned, we can separate the volatile fluorides and non-volatile fluorides. The non-volatile stays as like ash in the fluorinator, and the volatile we can condense them thanks to the different condensation temperatures in our condensers. So here are some pictures. The technology was placed in the alpha fluoride laboratories. The first thing from the left that you can see, maybe, yes, here, that's the fluorinator, the reactor itself, where the gaseous direct fluorination is occurring, and here are different condensers cooled to the different temperatures that are separating the products. And as I said, the main part and the main research that was happening in the past years here in Řeš was about the fluorination reactor itself, that you can see it in the different pictures, and actually the inside of the reactor on the right. So the next technology I want to talk about is the technology that was developed for Fukushima fuel debris processing. The CVR was contacted in 2015 by Hitachi to help them with the development of technology for the processing of the fuel debris in Fukushima plant, to remove uranium, plutonium, minor actinides, And at that time, here in the CVR, we were the only laboratory in the world that was capable and at the same time willing to work on such a project. The development and the active testing took place again in the Alpha Radiochemistry Fluorine laboratories in 2016 and 2017. Here on the big picture, you can see the fuel debris from the Fukushima power plant from the TEPCO websites. And the principle of the technology that was developed here was partitioning of uranium and plutonium again in the form of volatile hexafluoride, uranium hexafluoride and plutonium hexafluoride, and to separate them from all the melt, the corium that contained structural materials, cladding, parts of the fuel rods, and some other materials from the reactor core. Again, some pictures of the fuel debris from Fukushima. And here are the pictures of the preparation. The pellets were prepared that contained uranium oxide, plutonium oxide, americium oxide, also zirconium oxide, iron oxide, and parts of the stainless steel. They were prepared, sintered, and then the fluorination experiment was conducted. On the picture, on the bottom right corner, you can see the end product, separated mixture of uranium and plutonium. And the last topic in my presentation is the fuel cycle of molten salt reactors and the technologies that have been developed here in Řeš. The molten salt reactor program has been studied and developed in Czech Republic and specifically here in Řeš since year 2000. And right from the beginning, the activities included mainly the fluoride salt chemistry and reprocessing technologies. The main aims was to support the reactor physics and the neutronic studies of the fluoride salt. That was done by measuring in our reactors. Also, the application of the technologies within the molten salt reactor online reprocessing, and to verify some technologies that are connected to this molten salt fuel reprocessing. And the specific focus was on the thorium breeder molten salt reactor and its operation. The experimental verification of fresh molten salt reactor fuel reprocessing, specifically the synthesis of uranium fluoride, thorium fluoride, and preparation, the carrying, and then fuel salt that was flyby with the uranium fluoride and thorium fluoride was conducted. Also some theoretical and experimental development of the online reprocessing technologies like electrochemistry and again fused salt volatilization. And then some studies of specific aspects of thorium-uranium fuel cycle and its non-proliferation, physical protection, and stuff related to this was performed. Important part in the past times, in previous years, was electrochemistry of molten fluoride salt systems, and it has been studied in UJB Řeš, and again, the main interest was electrochemical behavior of the elements occurring in the molten fluoride salts, specifically uranium, thorium, and lanthanides as fission products. Also, the possibilities of electrochemical separation of these elements from the molten salt are studied. And some example of the last experiments that were carried out is the research of the flow sheets of the molten salt reactor online and offline reprocessing technologies, specifically the offline technologies for Japanese thorium tech solution. And last year's experimental verification of uranium removal from the liquid fueled salt for molten salt fast reactor was also conducted. A lot of this research is supported and connected with the projects supported by European Commission and Euratom, but also the national projects supported by Ministry of Industry, Ministry of Education, and also by Technological Agency of the Czech Republic. Yeah, and that's all from my side. Thank you for your attention. I'm sorry.
Thank you, Michal. Thanks a lot for your presentation. My question is to you, if you have any question here in the center. No? Yeah, there is one. Okay.
Do you have any actual information about next plan of Hitachi with method you have developed for the processing of debris at Fukushima?
Thank you for your question. Unfortunately, I do not have any current information what to do and how to approach the reprocessing of the fuel debris.
Okay. Yeah, I would like to ask, previously you had some cooperation with NRG. Yeah, we are still going to NRG Palace. It will be probably today. So do you have some further collaboration? Because they are also, NRG is dealing with the research for the fuel and salts and so on. Do you plan to? No, you don't have in this moment projects, so okay. So with that, thanks a lot to Michal for his presentation. And then we have the next presenter. Please, yeah, I could maybe remember. Wojciech Galek, I haven't seen. So, good morning. Maybe before I start with the slides, Wojciech could introduce himself, please, for you all. Thank you.
Okay. Thank you, Jane. Hello, my name is Wojciech Galek, and I'm the head of the Laboratory of Hazardous and Radioactive Waste Processing. We are just a small group in the CVR. We are sitting between the reactors, and we have few infrastructures and technologies for our disposal, how to properly process the mainly organic waste. Okay, so that was the just a small introduction. So what about the summary? I will show you the route of the processing waste, how the waste is processed within our lab and technological hall. I will show you what waste can be processed. Then I will start with the really interesting ones, as this is the molten salt oxidation, the MSO, then the evaporation technological line, which stands for the ETL, and then the stabilization process. So as I've mentioned, we are just a small group, and as we consist, we have the free apparatus or free infrastructures and technology, and with each technology we have also our laboratory equipment. As the molten salt for the processing of the organic waste in the beginning, then the ETL for reduction volume of the liquid waste, the inorganic and the organics, and also then on the end of the cycle we have the solid lidification line. So this is the waste route that I've put here to show you how it goes. So let's start from the right hand side. So about the organic waste, what we have. So the question is, what kind of waste can be processed? Well, practically everything, you name it. So from the ion exchange resins up to lubricants, oils, solvents, scintillation liquids and cocktails, to the PCBs, polyvinyl chlorides, etc. But I need to mention that every waste needs to be properly and fully analyzed. I will show you a bit later why, but it leads to the spenting of the salt in the molten salt oxidation process. So that was fast, but now let's go to the interesting part, to the molten salt oxidation. So what is the molten salt oxidation? As the name stands, we use the molten salts, mainly alkaline carbonates, the sodium carbonate mainly as the molten bath or the molten salt. It has its melting point temperature around 851 degrees C, and it makes us the bath where we put our organic waste. It means that the technology operates at the lower temperature than the standard incineration processes, and it has the ability to lower the volume of the organic waste, for example the oils. It offers the flameless oxidation, so it's less hazardous, and the high pH means that from the alkaline carbonates that it works as a scrubber for any acidic gases which can be contained within the organics. Also, as we have quite a lot of mass, it offers the stable heat transfer, and also it reacts as the catalyst-like environment. But as every technology, and the molten salt technology is not any special, we have a bit negative perks within the technology, and that means it's the strong oxidation environment due to the molten salts oxidation nature, etc. So there's the call for the need of strong and resistant materials which would be able to resist this environment. And in the end, we must ask the question, what to do with the waste salt? So in the principle, what is the molten salt oxidation? As I've said, or as you can see on the left-hand side, you have the picture of the one reactor system. The one reactor system is always good, right? You don't need to have two reactors. You have one mass of the salt. And as you can see, it goes from the yellow means the waste, and it goes to the one tubing, and the air is the small blue circles is going to the outer tubing. That goes to the bottom of the reactor and under the molten salt bath, which offers the longest reaction time, which is needed. And then you have the off gases which going out. So the one reactor system is good, but it was researched by the older people and more experienced than myself that there's lots of carbon monoxide and less carbon dioxide in the system. So if you can have high efficiency to turning the carbon dioxide from the oxidation process to carbon monoxide to carbon dioxide, you would need low dosing rates. And that means a low oxidation efficiency. That means increased time for the total oxidation. And in the end, it's really low applicability. So therefore, we have two reactors, which is much better, right? In the first reactor, you can have the primary oxidation. So the waste is turned into carbon monoxide. That goes into the second reactor, again under the molten salt, and with another air or the oxidation agent, it turns to carbon dioxide, which is much better. But it's, you know, it's less cost efficient, but it's really good. On the right-hand side, you can see the two-stage reactor system which we have. It's a diagram. And a bit more data about the molten salt oxidation. We have the reactor vessels made from Inconel 600. It was very affordable at the time, and it offers really good oxidation protection from the salt melt. Also, each vessel volume is 80 liters. It could be filled up to 40 liters maximum with the molten salt. And for the standardized waste, we are limited, or we can get only 100 milligrams per cubic meter for dry flue gas, which is very good. But it is also for the standardized waste, which needs to be properly introduced in the laboratory and few tests. You know how this goes. And the good thing is that as you have two reactors, you can have the two different temperatures, how to operate it. So, for example, in the first reactor, you can operate only at the temperature of 400 degrees Celsius, as you can use the eutectic mixture of alkaline carbonates, which is, for example, good for capture cesium and other volatile radioactive materials. And the second reactor can be operated at much higher temperatures to process the secondary oxidation to be more efficient. But in the end, each experiment and which waste are we putting inside the reactors, the salt is becoming spent due to the ashes or due to the acidic contaminants within the waste. And as the salt is spent, you need to properly dispose it. And you can dispose it by the small tubing at the end of the reactor, which is called the cold plug. And the cold plug is filled before the experiment. It's cooled from the bottom. And after the experiment, or when the salt is spent, this is coming from the fully analyzed waste, it goes to the water tank, which is under the two reactors. The water tank is filled with water, and partially the salt is dissolved after the pouring, and then you can process it in different technology, in the ETL, or to properly dispose it via the stabilization process. Now, at the beginning, what the organic waste is coming through our fuel cycle. So you have, for example, this beautiful ion exchange resins, and then you put it into the heated molten salt. Sorry. After some time, the salt is spent. You are heating up the cold plug, and this is how it looks when the cold plug is unplugged and it goes to the water tank. Sometimes you need to take up some samples. Yeah, that's really not some wanted work. And in the end, if you are going to the stabilization process, you will end up with like this material. And in the future, we want to have something like this. This is called the heat up discharge, and it is really good, but we are still going to it. Well, after the molten salt, how you process the organic waste, then we have the ETL. ETL is a pilot plant made of a series of elements able to process the inorganic liquid waste or semi-liquid waste, the ion exchange resins, and to reduce their volume. It is a modular system, so that means that each part of this technology can work autonomously, which is great, and it was fully developed for the volume reduction of the inorganic liquid up to the powder form, or to prepare the ion exchange resin to dry them up and put them into the molten salt oxidation. It needs to be really prepared for this process, so that means that there's lots of work in the lab, that's the left-hand side, and then behind the desk, because you need to really prepare for the process to know how much amount of water you can evaporate from the system to oversaturate it a little bit, but not that much. Yeah, it's a really long-consuming process. In principle, the ETL looks like this. You have the molten salt oxidation at the beginning, then you have the storage tank, vacuum evaporator. From that goes to crystallizator, up to centrifuge, the ion resins mainly going to centrifuge, and then the dryer, and in the end we have the stabilization. So let's begin with the storage tank. The storage tank is a large tank with 2 cubic meters. You can see on the side there's also conveyor for the preparation of the solution which we want. So it's for dried up salts, etc. And the tank is heated up for the dissolution of the solid waste. And it also works as for example, the pH adjustment. And if you want to prepare the liquid waste before the evaporator. Then we have this evaporator. It's 1.2 cubic meters large tank. It's 2-shelled. So in the outer shell, there's the hot water, which increases the evaporation. And also it's continuously stirred, which is great, and works under vacuum, which further enhances the evaporation process. The total tank is a bit smaller, so you can see from the storage tank to the vacuum evaporator, it needs to go into 2 phases. And after that, you have crystallizator. And now you can see the really difference between the volume. The crystallizator is still beautiful, but it's a really small tank. It has around 130 liters volume. It's also double-shelled, continuously stirred. And in the outer shell, there's the cold water, which helps the oversaturated solution to start to crystallize. But it's really hard to get to that point, or how not to fail that process, because when it's oversaturated, you start really fast cooling process, then it could really solidify up, and that's not really good for you and for my overtimes. And the next part is the centrifuge. It was one of the most expensive equipment we have, but when you do not oversaturate your solution, then you put it to the centrifuge and you will perfectly remove the solid part from the liquid part, which is great. And after that, you have the dryer. Also, you can see the drum for stabilization. The dryer is again 2-shelled tank. It has the capacity of 90 liters, and the outer shell help for the hot water to dry up the solid phase, but also it has the cooling tubing inside. When you properly heat it up, dry it up, then and you need to cool it down a bit for the stabilization process. And now we are going to the end of my presentation about the stabilization process. So practically everybody knows what should the stabilization process is, but it's the stabilization of waste or organic waste into stable form, which can be then put in, or is more able to be manipulated with and to put in storage. It lowers the leachability of possible contaminants, and it is necessary for the long-term storage in the repositories. We have the 3 main types as the bituminization, cementation, and vitrification, and there are 12 and more or less usable methods in our processes. In our lab, we are mainly focused on the geopolymer matrices. And this is, for example, the liquid waste stabilization, which was done in the previous project. It's not very common, but if you don't want to put your liquid waste, for example, the oils, into the molten salt oxidation, you can try to put them directly into the geopolymer matrix. We had quite good results. Well, not that good as if you put it through the molten salt oxidation, but still, it wasn't that bad, actually. So what stabilization we have done in our lab and in our group. So as I've mentioned, we are using the geopolymer matrices as we used mainly the geopolymer LK, which is the precursor Mephisto LO5 and then activator. We have taken that recipe and improved it a little bit for the LK10 because in the previous project our work was mainly focused on the stabilization of the salts from the molten salt oxidation, and we ended up with the waste loading up to 40% waste with the dry curing, which is very good. And also we ended to improve the molten salt oxidation waste into something called enhanced waste, which practically improved the final form of the stabilization. Then we have our solidification line, which is the end. Well, before was mainly put into the laboratory. Now we're going to the infrastructure. The solidification line is just a large mixer. Well, it's not just, but you know, we are using the waste drums with the 50 liters and 130 liters volume. We also have the drum trolley. It's on the left-hand side, showed in the furnace for the high temperature curing. And we can have the online temperature measurement, how to goes with the curing inside the drum to see how the temperature increases during the curing. And this is the end of the waste stabilization. So how it goes? Firstly, you take your drum, fill it with the actuator, then put your solid part in it. You have the drum on the trolley, which is self-rotatory, which helps during the mixing. You need to put the human strength in it, so you drive it in the large mixer and start the mixing. This goes for few minutes, up to 10 to 15 minutes for one phase. It needs to be filled several phases for each drum. So each phase took around 50 minutes, and you need to put more waste and more metakaolin in it to have to be properly filled. And in the end, it really goes down. But this looks the properly mixed stabilization product. In the end, you put the lid with the thermocouples to measure the temperature. This is how it looks like also when you measure the temperature on the side of the drum. And in the end, you need to look how beautiful work you have done also. That's really important. And this is all from my side. And on behalf of my team, I would like to thank you for your attention.
For your presentation, for a nice example of cooking in chemistry. I would like to ask, before I give the floor to others, what was the most dangerous or hazardous waste what you dealt with up to now? Or
well, it depends. As in the lab, we can currently work on the very low level waste, but mainly it's the treated ion exchange resin in the lab. But it's not that dangerous. I think that the most dangerous thing is in the molten salt oxidation. If you have the salt discharge, one of the photos was that we were brave enough at the beginning of the technology that we were standing very near, and after a few experiments we were just going further and further from it because we started the realization that it's not very safe. But that's the process is, and in the end we want to have the the solid phase removal. It was one of the photos. But the waste, yeah, it's nothing is that dangerous actually.
Thank you very much, and thank you for showing us your team and your facility and capability. It's very interesting, very nice to see it. So, is there anyone who has a question here in the room? Okay.
That's great.
That's great. It was very clear, probably, and very self-explaining. Thank you very much for your presentation. Okay. So, and before the coffee break, we have one more presentation, also related to the radioactive waste processing, this time of liquid radioactive waste. It's my pleasure to welcome here Anna, our colleague. So, as with the others, Anna, if you can say a few words about yourself. Okay, I will bring the... Okay, so please, Anna, floor is yours. You don't have to hurry. Explain us everything.
Yeah, so good morning, ladies and gentlemen, dear colleagues. My name is Anna Sees, and I'm here on behalf of our team to present our recent work on the membrane technologies for the liquid radioactive waste management. So before I dived in, I would like to start with the question. So why do we need some alternative radioactive waste processes? Why spend time and money to explore something new or newer while there are already well-established technologies such as ion exchange resins, evaporation and subsequent solidification either into the cementitious matrix or in the bitumen? And the reasons are that we are looking to lower the operation cost and overall energy consumption. Then also some waste streams are harder to process through the standard well-established methods. And also we need, some waste streams need to be processed more, and they have a bit insufficient quality to be then released into the nature. Another to recycle the boric acid, which is used in the nuclear industry, again to reduce the cost, and also the current emphasis on reducing the overall volume of liquid radioactive waste and a push for zero liquid discharge or near zero liquid discharge. Does this mean that we want to completely replace evaporation? Of course it doesn't, but what we would like to, we aim to add into sort of the group of the available technologies to process liquid radioactive waste when the evaporation proves a bit more costly or it's just not sufficient enough. So we were looking into membrane technologies. What are membrane technologies? It's an advanced filtration process. It uses a porous membrane, which then lets some of the molecules to pass through, for example, water or monovalent ions, while stopping the others, blocking the others on the other side. It's widely used in different industries, from food technology to pharmacy to cleaning or processing of the normal wastewater. It's very high efficient, it's flexible, it can be scaled up, scaled down depending on the volume you have or we have. It's got lower operation costs and overall energy consumption. And a big advantage that there is a very minimal chemical additive that needs to be used for the process. There's only a few chemicals that are used for the flushing of the membranes. So the membrane technologies could be divided into 4 groups, and it's based on the pore size or the molecular weight cutoff, as you can see on the picture on the right. And the main groups are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. The pressure-driven methods, so the smaller pore size you have, the higher pressure you need to apply in this process. As any technology, they of course come with challenges. One of them in the nuclear industry could be that because they're very efficient, that could lead to significant concentration of the activity in a very small amount, and this waste then could have a problem with current waste acceptance criteria. Again, it's sadly not as simple. It's still a complex process that needs to be tailored for the waste streams you have, or for the pyramid, for the resulting streams you want. And then 2 more technical ones, which is membrane fouling and membrane durability. Membrane fouling could be highly prevented by certain setup and by periodical flushing of the membranes. And then membrane durability. This is mainly in terms of the aggressive environments, such as low pH, like acidic pH, or on the other side also high pH, radioactive environment, and also high temperatures. So before I dive into the more technical stuff, I would like to explain how we started this research. So first we had to look into what's in the collection liquid radioactive waste tank in the nuclear power plants. We were looking at the national level and what feeds into it, what type of waste we could expect. Then over the course of the year we collected samples, we analyzed these samples to have an idea if it changes over the course of the years, how much does it change? Some of the average concentration you can see on the slides, they varied slightly over the course of the year, and they of course varied between the locations. And also the knowledge what is in the liquid radioactive waste then helped us design our model non-reactive solution, which we started with. We started obviously on the laboratory scale. We had various compositions of the waste. We varied the pH, the concentrations. We decided after the preliminary research to test nanofiltration and ultrafiltration membranes, and both dead-end and cross-flow setting. For those who are not really familiar with dead-end and cross-flow setting, the cross-flow setting, the result of cross-flow setting has 2 streams. One is the pyramid, and then the concentrate, where the blocked compounds are concentrated, and the dead-end is classic filtration, like your morning cup of coffee, for example. And then we also, because of the membrane durability, we tested the polymer membrane and the ceramic membranes as well. In this step, we looked into the total organic carbon reduction as well as a pre-treatment, because the liquid radioactive waste always have some complexing agents which are used for decontamination, or some surfactant which are used in the laundry or drainage cleans and similar. After the tests in the laboratory, we then moved to our scale-up pilot plant. We've chosen nanofiltration because we decided to prioritize the higher rejection rates, even though it meant that we will need a bit higher pressure to apply, which would lead to higher energy costs. Then the cross-flow setting, because the cross-flow setting lowers the probability of the membrane fouling. And then we tested two types of membranes, the tubular ceramic one, as you can see on the slide, and the spiral one polymer membrane. So the ceramic membranes should withstand more aggressive environment, like I said, low, high pH, and also the radioactive environment, but they are not that well established. They're not that well used, so we don't know that much about them. On the contrary, the polymer membrane are very widely used, but their resistance to the aggressive environment is not as good as the ceramic one. Before we did the test with the real radioactive solutions, we tested our scale-up plan with the non-radioactive solution. Again, we varied the concentration of the focus elements, which was cobalt and cesium, and then we increased the volumes of the process waste up to 150 liters, while we still have some work to do, and our top limit for the volume is 600 liters. The model solution, which was the non-radioactive one, the ceramic membrane had fairly good rejection of the cobalt. It was very low. It had very low rejection of the cesium, but this was to be expected because the monovalent ions, such as cesium, they tend to pass through the nanofiltration membrane. So we expected the rejection rate between 10 to 20%. But with the polymer membrane, we were very surprised, positively surprised, because the rejection of cesium was over 50%, together with the rejection of the cobalt, which was 100%. We also tested some other compounds just to see the overall behavior of the membrane. As I said at the beginning, we also tested this setup with the liquid radioactive solution. We had two types of solution. One was from the nuclear power plant, and the other one was from the experimental reactor. The ceramic membrane behavior was very similar what we've seen with the non-radioactive model solution, both with rejection of the cobalt-60 and the cesium-37. On the slide, you can see the starting activities of both radionuclides in the inflow feed. The polymer model performed much better, even in comparison to the non-radioactive model solution. Also, the cesium rejection rise to over 80%, which we're very happy about. What both membranes did, they also reduced the total organic carbon levels. The ceramic one from 40% and the polymer membrane from 65% and high percent. And we also finished so far finished experiments with the second radioactive solution, where both of the membranes had the rejection of cobalt, complete rejection of the cobalt, which was very good news for us. The cesium rejection for the ceramic module stayed similar as the previous experiments, while the polymer module also had as good as the previous one, between 70 to 80%, which when we expected 10%, we were very, very pleased about these results. We also started to look again into some other rejection of the other ions, just to see the overall behavior and what the resulting pyramid looks like. So what we've seen so far, it was that the polymer membrane worked much better than the ceramic membrane. Both membranes reduced the TOC levels, which could mean that there will be no pre-treatment needed to reduce the TOC levels. But we will have to perform more long-term experiments to see if the organic matter doesn't add to the membrane falling, which then would mean that we would increase the flushing amount and more often flush after smaller batches. While these experiments while these results are looking good for us at the moment, this is still an ongoing project and we have more experiments planned, and I hope I'll be able to share more results with you in the future. That gets me to the end of my presentation. Thank you for your attention, and I'm happy to take any questions.
Okay. Thanks to Anna. Thank you very much for your presentation. Towards morning, maybe somebody already woke up and would like to ask you something.
No, go.
Okay. If there is no question, next part of the program is the coffee break, and I would like to invite you there and discuss with our presenters further. Okay, thank you very much, Anna.
Thank you.
And according to our program, we have the next presenter, Tomáš Černoušek, also employee of CVR, and he's going to say something about the biological corrosion of carbon steel in deep geological repositories. Difficult one. Okay, Tomáš.
So, good morning, ladies and gentlemen. My name is Tomáš Černoušek. I'm from Research Center Řeš, and my presentation is aimed at microbial corrosion of carbon steel in deep geological repositories. The presentation is divided into four main parts. Firstly, I will speak about deep geological disposal in Czech Republic. Secondly, introduction of microbial influence corrosion. Third part represent electrochemical impedance spectroscopy experiment focus on microbial corrosion by sulfate-reducing bacteria and its result, and finally conclusion. So deep geological disposal in Czech Republic is based on Swedish SKB3 concept with certain modification. The deep geological repository will be constructed in a suitable granite environment at the depth at 500 meters with designed temperature of 100 degrees Celsius where expect long-term anoxic reduction condition. Canister will be consist of two layers. Inner layer, first inner layer of carbon steel, a second outer layer of stainless steel. As a buffer and backfill will be Czech bentonite representing calcium magnesium bentonite. Microbial influence corrosion is one type of corrosion that may limit the time of nuclear waste canister Also, the risk of microbial corrosion is low. The definite proof is missing. In the figure, you can see model evolution of temperature, relative humidity, and relative oxygen concentration at the canister surface with time. Based on this model, we can expect microbial corrosion at phase 4 under anaerobic condition during saturation of bentonite. Microbial corrosion or microbial influence corrosion represent influence of microorganism on kinetic processes of metals caused by microorganism adhering to the interface. Occurrence of microbial corrosion depend on type of material, environmental condition, and kind of active microorganism. The most dangerous microbial corrosion is for carbon steel, stainless steel, and alloys of aluminum and copper under stagnant water. At pH between 4 and 9 and in temperature range from 10 to 50 degrees of Celsius. The kind of active microorganisms are typical bacteria and fungi. General characteristic of microbes related to microbial corrosion, so they are small, often less than micrometers. Typical range is from 0.1 to 5 micrometers. They are ubiquitous in nature. They are resistant or tolerate a wide range of temperature, pH, pressures, and oxygen concentration. They reproduce rapidly under certain favorable conditions. Some bacteria can double in number during 20 minutes or less. So microorganisms can be classified different ways. In biology, is used three-domain system that organize biodiversity by evolutionary relationship. From corrosion point of view, is more suitable to classified microorganism by influence of environment. Here you can see classification based on pH, temperature, and effects of oxygen. For example, in effects of oxygen, we have obligate aerobes, facultative anaerobes, aerotolerant anaerobes, obligate anaerobes, and microphiles. Aerophiles, in case of obligate aerobe, they require oxygen but cannot survive without it, and facultative anaerobe use oxygen but can survive without it. Also, you can see the broad range in case of pH and temperature where can bacteria or microorganism can grow. Here you can see main microorganism, example of microorganism associated with microbial corrosion. There is 5 group. It's sulfate reducing bacteria, metal oxidizing bacteria, metal reducing bacteria, acid producing bacteria. There should be also fungi, and nitrate-reducing bacteria. More detail will focus on sulfate-reducing bacteria, which was part of experimental. So sulfate-reducing bacteria are assumed to be main microbial group causing microbial corrosion in anoxic environment. They are heterotrophic, facultative anaerobes. They can grow in pH range between 4 and 9.5. Typical temperature range for grow is from 5 to 45 degrees Celsius, but also exist thermophile sulfate-reducing bacteria that grow at least 70 degrees of Celsius. Some sulfate-reducing bacteria form heat-resistant spore. That means they can survive in dry environment. Here you can see corrosion mechanism by sulfate-reducing bacteria. There are some alternatives. In the figure you can see mechanism cathodic depolarization that was first description and published in 1934 by von Volzig-Kurt and van der Vlugt. They proposed that sulfate-reducing bacteria is responsible for removing adsorbed hydrogen that increased cathodic reaction and that led to increased anodic reaction and so corrosion rate. Another alternative mechanism are King's mechanisms in 1971. They show that also acceleration of corrosion is iron sulfate, which is more noble than iron oxide, and the corrosion was increased due to galvanic effect. Another mechanism is iron binding exopolymers. From 2002, there was shown that also part of biofilm that is extracellular polymeric substances also increase corrosion rate. And last is biocatalytic cathodic sulfate reduction theory. In 2010, it was shown that sulfate reducing bacteria can directly extract electron from the metal. So, initial stage of microbial corrosion is biofilms. Biofilm represent aggregate of microorganisms in which cell that are frequently embedded with self-producing matrix or extracellular polymeric substances adhere to each other or to a surface. The presence of biological film according metal surface does not introduce some new type of corrosion, but it's based on electrochemical modification of the electrochemical processes. So it's very hard to distinguish between microbial corrosion and corrosion. Biofilm on the surface doesn't not mean increased corrosion, but also biofilm can inhibit corrosion. On the figure you can see biofilm. It's a very heterogeneous surface containing metabolic product, crystals and organic matter. The biofilm you can see life cycle of biofilm in 3 steps. So first part of biofilm growing is attachment, the initial adhesion and conditioning film. Second step represents growth of colonies during which is increased the thickness of biofilm, and last step representing seeding dispersion that could lead to a secondary layer of biofilm, as you can see later. In the figure you can see biofilm on carbon steel with local attack. So just now you can see electrochemical impedance spectroscopy experiment under laboratory condition for study microbial corrosion by sulfate-reducing bacteria. We use carbon steel. The experiment was ongoing under anaerobic condition in glow box. There is concentration of oxygen below 1 ppm. As an environment was anaerobic natural groundwater dominated by sulfate-reducing bacteria, mainly the sulforomicrobium species and the sulfovibrium. Also, we tested negative, it was ongoing negative control without microorganism to see how influence of microorganism on corrosion rate. Here you can see experimental setup by electrochemical impedance spectroscopy. The amplitude was 10 millivolts. The frequency range was from 100,000 hertz to 5 millihertz. In case of biotic environment where was a microorganism, we have to reduce frequency to get information about corrosion rate. As analytical methods, we use next generation sequencing and real-time qualitative PCR. So, and just now you can see a result from experiment. There you can see time evolution of electrochemical impedance measurement of carbon steel under abiotic condition. This means without microorganism. You can see in the figure that represent impedance spectra in a Bode diagram. During the whole measurement, we use only a very simple equivalence circuit. And you can see that the shift of time constant is slowly down to lower frequencies. This means that the corrosion is slowed down, and we don't observe second time constant that deal with oxide layer, so the corrosion was in active state without protection oxide layer. On the contrary, in biotic environment, we observe time evolution of 3-time constant. Second time constant was observed after 560 hours, and third time constant was observed after 2,700 hours. We identify at the end of experiment, as you can see on the SEM micrograph, that this time constant deal with 2 layers of biofilm on the surface. So, and there you can see that polarization resistance and its time evolution. At the end of experiment, you can see that under abiotic environment, the corrosion is lower, and so we see increased corrosion rate by a microorganism. At the end is by factor 2. This indicates that this corrosion rate is not destructive as biofilm that is under aerobic condition. So some analysis show that abiotic environment is, it was very simple surface. The surface was covered only ferrous corrosion products. We don't detect any sulfur. In case biotic environment, you can see the very complicated surface, pom-pom shape with many bacteria from second layer of biofilm. And also it was confirmed presence of sulfur. So microbial analysis confirmed that in the biofilm and environment at the end of experiment dominate their microorganism sulfate reducing bacteria. So the corrosion increase was due to sulfate reducing bacteria in the system. So finally, conclusion, our experiment shows that it was only under anaerobic condition, strict anaerobic condition, the corrosion is not so aggressive as in case when biofilm start grow under aerobic condition. Also, electrochemical impedance measurements shows we observe by this method the growing of biofilm in 3 steps, and microbial analysis show that the main microorganism was sulfate reducing bacteria, which increase corrosion rate. So that's also from my side. Thank you for your attention.
Thanks to Tomáš. Thank you very much for your presentation. Very interesting to see how the living matter enhancing the corrosion. And even better, it was a very nice example how you can describe with the electrochemical methods and the imaging methods, CM and our infrastructure, very nice phenomena of this. Yeah, thank you very much. And other question? Oh, great.
Hello, good morning, Tomáši. I have only a simple question. Do you cooperate with Technical University Liberec? Because Liberec is studying microbiological conditions in the host rock environment.
Yeah, in this study we cooperated with Technical University of Liberec, so they do it microbial analysis there, and yes, we have very nice article.
Okay, there is another question. So it seems that coffee helped you to be more brave.
Okay, thank you very much for your great presentation. Just two short questions. The first one is, what type of coating could prevent this microbial corrosion to increase the resistance, if possible? And the second one is, during your experiments, you've dosed only the sulfur-reducing bacteria or some kind of, bacteria?
So second question is there. So it was natural environment, anaerobic water. So here you can see community which was in there. Yes, the sulfomicrobiome. This is microorganism of sulfate reducing bacteria. You can see in heat map that the amount is very high in biofilm and also in water at the end of experiment. So this indicates that this sulfate reducing bacteria increase the corrosion rate. And first question was about what is main reason for increased corrosion.
No, that was if there's some kind of protecting layer.
Protecting layer, because the protecting layer is maybe by resistance of biofilm. Maybe the microbial community is not active for corrosion. Yeah? So because you need to have active microorganism, they do its corrosion. So if you have a microorganism on the surface, it doesn't mean that they do it microbial corrosion.
Okay, great. Thank you very much.
Thanks for your question. Is anyone else about to ask? If not, thank you, Tomáš. Thanks one more time for your presentation. And next presenter on our program is already coming, Zbigněk Hlaváč. Also our colleague from CVR.
Thank you.
And previously we heard something about corrosion or degradation caused by microbes. Here we will hear something about degradation of concrete. Floor is yours. Thanks.
So, hello, my name is Zbigněk Hlaváč, and I will be talking about some of the results of Europe project H2020 in the cooperation with CTU and UJV. We were working on the cement concrete matrices. So I was working in work package 3 CORI, which is cement organic radionuclide interaction, and especially CBR was participating in tasks 2 and 3. So task 2 was about the degradation of some organics, and task 3 was talking about the cement organics interaction. We were not participating in the last task, which was most interesting for example, swell lava. So this was about the radionuclides organic cement interactions. Our colleagues were from UJV, as I told so. So there was Petr Večerník. From CTU, there were Barbara Držinová, Jan Kozenfeld, and also from the civil engineering faculty, there was Radek Vašiček. And myself, I was representing CVR in task 2 especially, and task 3. So a little bit about the purpose of our work. So the basic idea was that there are some, let's say, organics in the waste repository, and the organics can have some effect on the, let's say, on the future, on the radionuclides, on the transport, and all the interactions. So what was our task? So we are thinking that in the cement matrix, there is, for example, plasticizer, which is organic compound, and it can be degraded by radiolysis, hydrolysis, and the product of the radiation can have some influence on the future behavior of the atmosphere. Also, we were trying to work with Sural, where they provided us the concrete from Rickert repository. And also we got some compounds which were acting in the drum-in-drum system of the repositing of the radioactive waste. So a little bit more about task 2, 3, and 4. So what was done there? So in task 2, we were working with plastificators, ionesis, and sorbents, and we were irradiating. And people from CTU, they were doing the hydrolysis. This was task 2, and it was only about pure organics, with no cement and no hydroxys. About task 3, so we were working in cement, concrete materials. There was hardened cement paste, for example, and concrete from the Rickert repository. And we were doing also the irradiation and hydrolysis. And at the last task where we didn't participate, not so much, so there was the radionuclides interaction, migration, and also with the influence of the radiolysis and hydrolysis. So a little bit more deeper to each of the tasks. So about the task number 2, so the work was to prepare some samples of the organic compounds and let it be aged, let's say, by radiolysis, hydrolysis, and to try to find the final products of this, of this aging. It was impossible to get the final formulation, for example, of the plasticizers, super plasticizers, which are being put into the concrete. So finally we decided to make our own compound, which was called PAN, P-A-N, and we knew, let's say, exactly the composition of this compound. So in here I will be showing few results. They are very complicated compounds, the formulations of the plasticizers in concrete, and everything is kept in some kind of secret. So we are not able to get the exact formulation before radiolysis, and afterwards not as well. Nevertheless, we are trying to make the radiolysis with some levels of degradation. And here you can see some mass analysis. And what I can say, so the final products are very much complicated. You can see on the right-hand side that it is no methane, it is not propane, whatever. This is some kind of phthalate, and it is really very much complex. Because of that, we used the PEMS, as I told so. We are trying to also treat some sorbents by the cobalt-60 source of radiation, of gamma radiation. So in here you can see the results where we were maybe able to find what are the products of the radiolysis. And it is after 1, 2, 4 megagrays and 8 megagrays. So finally, after 8 megagrays, let me have a look. So there are some peaks which say that there is some product, for example, amide or nitrite or some others. So in some cases, it was possible to find some products of the radiolysis. Especially in here, it is quite clear because you see the clear peaks of the mass spectrometry, and those are on the right-hand side. Those are the products which just were observed in the product. There is also not only radiolysis. I was talking also about hydrolysis. So in here, the products were a little bit less complicated. Nevertheless, you can see also very long chains of the polymers. So also this was a little bit tricky, and finally it was not easy to evaluate all the results. So let's go to task 3, where there was the cement-organic interaction. So in the task 3, we were working with concrete, with hardened cement paste, and also with the plasticizers and with other compounds. What was some benefit, because during the kickoff meeting in Barcelona, so Zdena Lahdová from Surao just advised that all the partners of all the projects, there were about 12 partners, will be using some basic material, and the material, nobody knew what should be the basic, the basic level, and we decided it will be our concrete, our cement, CEM1, which is the Portland cement. This was very important for Surao because they are using this cement for fabrication of their drum system, and in that case, all the Europe was working like for us, for Surao. What some of the results from task 3. So I will start with the picture on the top left. So there are some. It is the view of our gamma chamber. So those samples on the right side of the picture, those come from the UJV. Oh, thank you. Then there are some more samples on the top. The samples come from the nuclear faculty of CTU. So those couples, they come from the task 2, so it's the degradation of the organics. But there are also some small slabs, the very small slabs as such size, and they belong to task 3. So firstly, we were measuring those by non-destructive testing. Then we had some reference samples for destructive testing, and then we had samples for the radiation and afterwards testing. So this test is about the rigidity. It says I will damage the sample by some load, and I'm measuring the displacement. On the graph in the middle, so I'm showing the load of the destruction, but I'm also showing the displacement or the rigidity. The black points, they represent the samples without radiation, and the green one, they represent samples irradiated by 7 megagrays. And you can see that, for example, for STEM without plasticizer, it says that the load is a little bit the same, but the rigidity, like modulus of elasticity, more or less, let's say, call it rigidity, is higher. So in this case, it says that radiation didn't pollute the material. Maybe some of you were yesterday on the speech of Patricia Halodová, so it was more or less the same, that in some cases radiation can help to the concrete, some cases it can damage. Also on the top, I don't see myself. So there are also some samples with plasticizer, but also in this case, either irradiation didn't cause any change, either, or it makes some profit, it went better. In case of some simple aging, it is on the right-hand side. So the aging was more or less the same, that the older was the sample, the better were the properties of the sample, rigidity or strength. Strength was tested on the cubes and rigidity on the small slabs. So this is finally my slide, because those were somehow done by the cooperation with my colleagues. So on the right-hand side, there you can see some visualization of nonlinear wave modulation spectroscopy on the top. So I can show there is a sample without damage, and you can see the frequency spectra. That means frequency is on the horizontal line, amplitude on the vertical, and if there is no damage, there are not so many peaks. So in this case, there is one and second one high peak. Those were like done artificially, let's say, and they mean that there is connection between the transducers and the sample. But if there are some more peaks, for example, some intermodulations, it means that there is some pollution in the sample. There is some non-linearity or cracks, microcracks. So when there was sample without irradiation, it was the small slab, this size. So the sample, there are no special peaks. Sample with irradiation, there are some peaks, and this is sample from the Ricard repository, and there are also some peaks. More or less, it says that there are non-linearities and there are some cracks, microcracks. But let's say concrete is not simple material, and if I cast a concrete, if I prepare some sample, there is some maybe crack, there is non-linearity. On the bottom, you can see a table. When I proof a glass, there is nearly no non-linearity, because if I just load the glass and see the stress-strain curve, it is linear, and suddenly there's fragile crack. So the non-linearity of glass is very, very small, or nearly no. When I use some steel, maybe carbon steel, also the non-linearity is very low, because there is a stress-strain diagram, there is load increasing, displacement increasing, there is some yielding stress, and then it is damaged. Nevertheless, I'm checking the initial of the stress-strain diagram. But if I'm testing concrete, even it is healthy concrete, there is some non-linearity. You can see also in here or in here. If the concrete is a little bit damaged, non-linearity coefficient is higher. If it is very much damaged, it's even much, much higher. It means more than 1. So let's go to the left-hand side picture. When I was testing a sample with plastificator Isola, so before irradiation is the blue one, after irradiation is the orange one, it's increasing. There are more cracks. The same with the plastificator isoplast. The higher irradiation, the more microcracks. When there is no plastificator, suddenly there are not so many cracks. And Ricard concrete, luckily we don't have the reference number, but I can say that the concrete after irradiation, it has 0.05 or 6 beta nonlinear coefficient, which says there are some cracks, but it's healthy anyway. So this is nonlinear modulation spectroscopy. On the left-hand side, on the top, so there is a simple ultrasonic testing, and it says that I will send ultrasonic signal through a sample, and I'm measuring the time of the transmission, and I'm like calculating about the modulus of elasticity. And you can see that when there is no plastificator, there is very small there is a plastificator isola, there's very small decrement of modulus of elasticity by radiation, plastificator isoplast, or when there is no plastificator, so there is higher decrement. Then we were testing Ricard concrete. There are some small changes because some samples in the middle, they were not covered by aluminum foil, so it was a little bit different condition than the last sample, which is the green one, which was covered by the aluminum foil. Nevertheless, either or, there was no decrement of the moisture in the sample. The moisture is represented by the dashed line. So in the samples with plastificators, there was some decrement of the moisture during irradiation, of course, because it was not covered sample by anything. It was simple. And in the case that there was no plastificator, the sample lost a lot of water. Also, you can see on the right-hand side, so when we did the rigidity test on the Ricard concrete, so there was small decrement of the rigidity after irradiation, which is also like shown, sorry, I cannot find myself, in this column or that column, the green one. Okay, I will skip this one. And now let's start and end with the last task. CVR was not participated in this task. Nevertheless, it is the most important one. So in the first or second task, we were trying to find the things that are the products of the irradiation or hydrolysis. So we found that there are some phthalates, adipates, some other compounds. In the task 3, we found what is happening when I add cement matrix to the organic compounds, and in the task 4, it was like some result of all the investigations, and we are trying to find what is the migration of the radionuclides with or without organic compounds. And the basic idea was and is that if I add organic compound, for example, to uranium, for example, phthalate, so it can be transported by higher velocity through the material. I can say that during our investigations in Korea, we didn't find any such a result. Nevertheless, in the literature, we can find that, for example, technetium, it works with some organics, and it can be either improved, either decreased the velocity of the transmission through the engineering barrier. So that's all from my side. I thank you very much for your listening, and I'm open for any questions.
Thank you very much, Zbigniew, for your presentation. Must just underline that being part of the EURAT whatever how you pronounce it. Big European collaboration on radio waste management is important, and you are doing great job in that group. So if somebody has some question? Perfect. But for people who are maybe listening us connected, it's better. Thank you.
I would like to know whether there is also some sign of polymerization during the radiation treatment of the superplasticizers and.
Of course, there is polymerization. As I thought before, I will show once more. So we can call this as polymerization. As I thought, it is so much complicated, the compounds, that we are not able to just to analyze it. So the chains are so long and so difficult.
Do you think the splitting short parts of compounds is dominating over polymerization, or polymerization is an important part of the process of the radiation, maturation of the...
It can depend also on the temperature and the acidity and other effects. So I think everything goes together. And it's possible that, for example, higher temperature, lower temperature would omit polymerization or something like that, but this was not investigated there.
Thank you.
Thank you.
Thank you. Anyone else would like to ask something? It seems not in our room. We also don't have question from people online. So thank you very much for your presentation. Yeah. And before we wrap up this part of the day, we have another guest. Please, please welcome here Mr. Radek Trtílek. He is the head of the division of the radioactive waste and disposal in our mother company, UJV. So if you can say, please, some words.
I will speak to this microphone.
Yeah, and I will change the presentation.
Yeah, thank you. Good morning, or I think now is good afternoon to everybody. My name is Radek Trtílek, and my presentation is not result of any research projects, even it is not any rocket science, but more engineering and informative remarks to the waste management policy updating, which is just now ongoing. And I want to mention some of important conceptual issues which follows from this waste management policy updating.
Yeah, it seems that okay. Thank you.
Thank you. What about scope of my presentation? I give you some background and introductory remarks. Then I focus my speech on policy updating about aspects which must be taken into consideration and which assumptions are base for this updating. And there is from this policy updating, there is many interesting outputs, but I focus my presentation on, from my point of view, the most interesting facts regarding inventory of spent nuclear fuel and low-level wastes for final disposing in the future. And what follows from these aspects and from these results, it is issues and challenges for future solution, and then something for conclusion. What is the policy of spent nuclear fuel and radioactive waste management? It is conceptual document, which on conceptual level solved for all existing and anticipated radioactive waste streams their way and the options for their management from generation to the final disposal. Policy has legal base. This base is set by the decree on the policy, which follows the Atomic Act, and the decree is based on the European Directive on Responsible and Safe Management of Spent Fuel and Radioactive Waste, which is directive issued by Euratom 13 years ago. The responsible for preparation of the policy is Ministry of Industry and Trade, and the policy itself is approved by government. For each updating of the policy is in the beginning prepared comprehensive background study, which is source of all needed information and relations between this information, and this background study following previous updated state energy policy or conception, and follows the valid deep geological repository development schedule. And the history of the policy is the first policy was approved in 2019, and this policy is still valid, but the comprehensive study for it was prepared, and base for it was prepared in 2011-2012, and the time between preparation and approval is so long because this first policy was evaluated in strategic area assessment and also in the cross-border assessment with neighbor countries. Updating of this policy was prepared 4 years ago, in the beginning of or before COVID, but without final discussion and final approval. This is due to the adoption of EU resource taxonomy, which was approved in this time, and for this reason the finalizing was stopped, and this job was renewed this year. The comprehensive study was issued and taken over to governmental bodies, and now is in progress preparation the final document, which is expected to be approved in the government in the beginning of next year. Which aspects were taken into consideration? There are many groups of aspects. One are strategic matters or strategic kind decisions about preparation and construction of new unit in Dukovany 5 or Dukovany 2, and about future deployment of SMR units. The second important strategic decision was reducing of a number of potential sites for siting of deep geological repository, which was made in the end of 2020 or beginning 2021, from 9 to 4 sites, investigated sites. and decision of nuclear operator about extension of operation existing Dukovany and Temelín units. In the past, we evaluate two options, shorter and longer term of operation of these units, but now is taken into consideration only 6 year operation. 60 year of operation. The next important aspects are legal and regulatory matters. New Atomic Act, it is from 2016, but the following regulations and decrees has 10 years. Some of them have 2 years for implementation. The new European regulation on taxonomy of energy sources in the beginning of this year was issued and approved. New act on procedure related for on siting to deep geological repository, and also updating, currently ongoing updating of state energy conception or policy and national active plan for nuclear energy. Next aspects are international evaluation missions, which were running last year, and public consultations of existing policy and fulfillment of existing policy, which took place in the beginning of this year. And there are also some technical challenges on projects and changes, which is also important for this strategy and policy updating. And this is one of the most important, is a reconstruction of technical infrastructure, enlarging and modernization of Richard repository for institutional wastes, and also modernization of long-term buffer storage and reloading site here in UJV Řeš. The next important technical aspects is repatriation of high enriched uranium from LVR-15 reactor to Russia, and preparation for future return of high-level waste from its reprocessing, running EU R&D projects, newly approved and issued R&D plan in the field of radioactive waste management, including using of underground research laboratory Bukov, and is running, and it is continuing, continuous process, is expected finalization of selection of deep geological repository and high-level disposal, final high-level disposal, and initiation of preparation of its construction. The chosen of final site, it's expected until the end of this decade. And other important aspect is that is still continuing the EC infringement procedure regarding the current policy, but it is more technical or formal aspect than the real new requirements. The assumptions for updating, I think it is for you probably clear. Operation of existing units for at least 60 years, and the preferred option for future decommissioning is deferred dismantling. And operation means including of existing radioactive waste management infrastructure. Next technical assumptions is operation of 4 research reactors, 2 here, 2 in Czech Technical University in Prague. Operation and existing of 3 near surface or near shallow repositories. The fact that the spent nuclear storages are decentralized on the site of nuclear power plants, and here in Řeš for fuel from research reactor. Important assumption is to calculate with 4 planned large or conventional big units of EPR 1000 with future preferred option for decommissioning as immediate dismantling, and also expecting or plan for deployment of up to 3 gigawatts of SMR units. Important assumption is also that the valid plan for starting of DGR in operation is in 2050. The 50 itself is not realistic. Realistic is if we analyze the critical path 2052, but the second question is if it is needed. And also the using of radiation sources will continue as before. And now some results or information, resulting information. There is inventory of spent nuclear fuel and intermediate level wastes from decommissioning, which must be also finally disposed in a deep geological repository. You can see as existing units as expected for new units, and also SMR expected equal 6 to 9 units, and also non-power sources, which must be finally disposed in DGR. The SMR line is yellowed because this is important from point of view of designing of deep geological repository, because all previous designing studies or feasibility studies and all preliminary safety analysis was made for 10,000 tons of heavy metal, and the increasing for which these plans for or by 40% is relatively very high, and it must be very carefully investigated on investigate candidate sites if this amount of heavy metal could be disposed in these locations. For choosing and evaluation of these sites is many criteria, but it will be not so good if this criteria will be only one which this criterion will be only one which will decide on it. This is similar table, but for low-level waste inventory for disposing in existing repositories. There is important result, and I also show it on the next slide on the graph. Amount of wastes not only from operation but also from decommissioning. It is very important to take into account that from decommissioning the amount of wastes is practically equal to amount of wastes from a normal operation. And you can see that there will be needed for future needs almost 180 volts. The repository, existing repository has 112 volts, and 28 of it is filled to this day. Regarding Richard repository, also I have on some next slide graph, it will be clearer with these graphs. On this graph you could see the filling during time of Dukovany low-level waste repository, and I will comment what I show you from the next table. The red line is total volume of the repository. The blue line is filling by the wastes from existing units, including wastes from their decommissioning. It means that for existing units it is enough, the volume. The yellow line is contribution of future SMR deployment. Light yellow is operation, deep yellow is from the commissioning, and the green line is all together including 4 new big units. And you could see that, or can see that there is between blue line and total this volume which is for disposition is 19 volts, and it is just for one EPR 1000 unit. And it means that if the plans for deployment of new units, despite the fact if it is SMR or big units, the space is not enough and must be in right time solved. On the other hand, we have for the decision what to do 30 years. But on the other hand, the preparation of any nuclear installation is very long, and it is need to follow it and to regularly evaluate this filling graph. In this slide is the same for Richard repository. You can also see that during 30 years the space will be fully used, and also there will be question what to do. What are challenges and issues for future following these graphs and tables? That is needed to evaluate and very carefully investigate if there is all spent nuclear fuel in future disposable in host rock in now for evaluated sites. It's one. The second, to study and to do some feasibility study, it will be useful to centralize as facility for processing of radioactive wastes from future units, mainly if will be used mobile technologies, and also used these mobile technologies with advanced techniques, and also is reasonable to investigate and evaluate if could be centralized also mainly for SMR units, spent nuclear fuel storage. And is needed to regularly update Dukovany repository filling model. The question could be if we set into operation in 2050 the deep geological repository, maybe the enlarging of Richard repository and Dukovany repository is not or will be not needed. And as summary and conclusion at the end, despite the way and options of future development of nuclear energy, the infrastructure for spent nuclear fuel and waste must be provided in necessary capacity and in necessary time. The criterion for the final DGR siting, that must be investigated disposal capacity for all expected fuel and high-level wastes. I think it is probably impossible to plan 2 different deep geological repositories within the territory of the Czech Republic. And regarding the Dukovany repository for normal operational low-level wastes, the existing vaults and existing repository is enough for all units under operation, and also for 1 additional new, for example, APR 1000 unit, including the wastes from their decommissioning. But if we decided and if we really deploy any other big or SMR unit, it will be needed, really needed, and it will be condition for siting and starting of construction of some such unit to decide what will be do with Dukovany repository, or if the wastes will be disposed in DGR. This is all from my side. Nice picture, like joke, not vision. And thank you very much.
Thank you, Mr. Kudilek, for your presentation. We have a question there.
So thank you, Radek, for your information about the current status of the situation in the waste situation. Yeah. So, okay. So you know me, so you know that I am not in favor of the building of underground repository. Yeah. And,
yeah, I understand.
My dream is to close the fuel cycle and not to continue in once-through fuel cycle. So I suppose you are in the team of persons who prepare the actualization of the policy. Yeah. So therefore, I have a question: if there are also some discussion about the closing of fuel cycle in combination that we plan to build new reactors in Dukovany and later on in Temelín, yeah, that those reactors should be able to accept MOX fuel. By the way, for the audience, when I had some presentation about closing the fuel cycle, and there were also persons from top management of Ravra, so nobody has information what is MOX fuel. So I was surprised and maybe happy. In European Commission taxonomy, yeah, there is some information, some paragraphs that the countries should be ready to have underground repository till 2050. Yeah, but in some other paragraph, there is also information that the countries should do maximum to decrease the amount of spent fuel or radioactive waste, and also that they should adopt the partitioning, transmutation technologies, and so I mean the close the fuel cycle. So therefore, I would like to ask you how it should be implemented in Czech Republic, yeah? And if there are some discussions in the preparation of the new policy, yeah, to close the fuel cycle in the future.
It's a very good question, and maybe for different discussion than is this conference. I am not sure if I'm authorized to speak about my opinion and about official opinion. In the background study, we included the chapter which you prepared for us, and we also wrote some articles about potential closing of fuel cycle and about reprocessing and MOX, but I cannot say which stakeholder, but one of the stakeholders which is involved in preparation of this policy on each meeting said why you wrote it in this fairy tales, how you wrote it in the, or you are writing it on the paper.
Generally, it looks, if we will be able to close the fuel cycle, so it will be necessary to have from additional 4 reactors at minimum 2 able to accept MOX fuel. We will need the underground repository after after 2120.
Yeah. There in the Czech Republic. I agree with technical arguments, but there is no common will of all involved stakeholders to plan it and to think of it. Yeah. There are, one of these stakeholders is too strong to be able to go over his opinion. And more in Czech language during coffee break.
I agree about that. We are getting on the hot ground. So thank you very much for your presentation. Thank you.